The following slides will be about the teaching model by competencies, or which is the same, learning how to think. We'll show some of the different ways this model could be used and, of course, we'll give some examples, as well as some suggestions to make it work. Keeping always in mind that understanding is a pleasure. The main goal of teaching competencies is making the students competent to solve a real-life problem. We can reach that on the teaching physics context. In order to solve a physics problem, it is important to think. Learning was focused on memorizing in the past, but now that technique has become pointless. First of all, media has made the information so easily available at any time. One of the most important tools is the internet. However, students must be careful with the information they choose, because it could be real or fake. The teaching process could help them with that, and of course, they need to understand the information they are getting. A good way of distributing the time of the class would be according to the days of class and the topics that we want the students to learn. In order to do that, we could follow a book and distribute time over the chapters. Also, there are some topics that will need more time than others, and that is because they could be more relevant to life or because they are more complex to understand. Before teaching comes the evaluation. Tests should be designed before teaching them, and they must include questions that will reveal whether the students have learned or not. Each question defines an objective, and the grade will tell us whether if it was accomplished or not. With all that, the designing test process it's not easy. Moreover, questions that measure the student's ability to think are difficult to formulate. We recommend from 25 to 30 questions per chapter. Now that the test is made, we can think about how to teach each question on it. Those questions could lead us to different methods. For example, induction, deduction, analyzing discrepant events, and from real life. The next video will help us to understand the first example. Light ball over a heavy ball. Lighter ball bounces faster than the heavy one. Zoom in. Each ball gives its kinetic energy to the upper one. First, let's explore the deductive method. Let be two balls at rest. Ball 1 is over ball 2, and at the same time they are released from rest at some height h. Thus, by energy conservation, we know that the kinetic energy of each ball when the balls reach the ground will be related to the initial potential energy by equation 1. Also, the kinetic energy before touching the ground and just a moment after must be the same and only kinetic. This is stated on equation 2. On the left side of the momentum conservation equation, labeled as equation 3, ball 2 has already touched the ground and it's moving upwards, and ball 1 is about to crash into ball 2, but not yet. On the right side, ball 1 and ball 2 have crashed and the kinetic energy has been redistributed on the system. After some algebraic manipulation, we get an equation for V2 and an equation for V1. As we analyze whether we take the sign positive or negative for V2, we notice that if we pick the positive sign, then the velocity of ball 2 will be the same that before the impact. So by momentum conservation, this will imply that the velocity of v1 is minus v, which doesn't make sense because ball 1 is over ball 2, and if ball 2 is moving upwards, so do ball 1. Now let's pay attention to the equation of v1. On the limit when m1 tends to 0, the magnitude of v2 is just the same before the impact, but the magnitude of v1 is 3 times that. For the particular configuration in which the mass of ball 2 equals 3 times the mass of ball 1, If we substitute that on equation V2, we see that V2 is 0. This means that the ball 2 will stay still on the ground. The following information we got it from Popular Science, and it explains some of the physics of a car crash. There are two important times here: 900th of a second, when the crash finishes for drivers not wearing a seatbelt or without airbags on their cars, and 1500th of a second, the time in which the crash finishes for the occupants wearing a seatbelt. It seems a very small difference, but in a car crash, this time difference is really important. We'll see why. Let's suppose that the initial velocity was 15 meters per second. Without wearing a seatbelt or airbags on the car, the occupants of the car will suffer an acceleration of 17 times gravity. This means a force of 17 times their weight. But wearing a seatbelt reduces the force to only 10 times their weight. On this graphic, the blue points plotted represent the time on the x-axis and the velocity on the y-axis. However, on time 200th of a second, there is a big jump on the velocity, so we interpolated that point by fixing a curve with the other points. This would be the red curve. What happens in a car crash? This slide is from another website and has fake information. Can you guess it? It reads, "In class, you've observed clips of car crashes, but these cars were going only at 30 miles per hour. If a driver is not wearing a seatbelt or if the car doesn't have an airbag, then when a car is traveling at 55 miles per hour and hits a solid object, the following happens. 1/10 of a second, the front bumper and grille collapse. 2/10 of a second, the hood crumples, rises, and strikes the windshield. The spinning rear wheels lift from the ground. Fenders begin to grab themselves around the solid objects. Instinct causes the driver to stiffen his legs against the impending crash. They snap at the knee joint. The passenger compartment is still going at 55 miles per hour. 3/10 of a second, the steering wheel starts to disintegrate and the steering column aims for the driver's chest. 4/10 of a second, at this point, 2 feet of the car's front is wrecked. The rear is still moving at 35 miles per hour. The driver's body is sliding forward at 55 miles per hour. 5/10 of a second, the driver is impaled on the steering column. The blood rushes into his lungs. 6/10 of a second, the driver's feet are ripped out of tightly laced shoes. The brake pedal snaps off. The car frame buckles in the middle. The driver's head smashes into the windshield. The rear wheels, still spinning, fall back to the ground. 7/10 of a second, hinge ripped loose. Doors fly open and the seats break free, striking the driver from behind. 8/10 of a second. The seat striking the driver does not bother him because he is already dead. From 9/10 of a second to 1.2 seconds, the last 3/10 of a second mean nothing to the driver. If you find this frightening, look at more car and driving information from the Idaho National Engineering Laboratory, the source of this timeline. Well, the wrong information is that the car crash lasts 1 second. If it was 1 second, the force of the impact would be more or less like the weight of the driver, which is nothing for a car crash. Let's think of an example on real life. Imagine that you are driving and then all of a sudden a truck appears and stops. You have two options. You could full brake or turn the wheel so that friction stops the car. With that distance, you could stop the car and not crash with such a high velocity. If you turn, you won't dissipate any energy, because the centripetal force is normal to the trajectory of the car. Now you know what to do. I hope you never need this information though. Constructivism. With this technique, we need some foundation to construct knowledge. It is possible that students already have information about the topic that is going to be taught. But how can we find out the students' preconcepts in the allowed time? Organize a question storm about the topic. Ask students to write their answers and then read the most relevant ones. Also, clarify those which had a wrong answer. And of course, never mention the student's name. We don't want anyone to feel humiliated. We all remember a few very good teachers, mainly because of the way they taught. Those teachers touch us so much that they have somehow influenced our lives. Maybe we've chosen our career or work because they have inspired us. As an example, Excel is a tool that, used with creativity, can help us to solve problems that we wouldn't have imagined. In this experiment, I asked my students to use a compass in order to follow and draw the field lines caused by the interaction between a magnet and the magnetic field of the Earth. The results are the drawings on the pictures. If we want a more accurate solution, we could compute the values of the magnetic field using an iterative process in Excel. The equation of the magnetic field is the one that we are going to iterate. Notice that this expression is written in polar coordinates. However, the vector sum necessary for the iterative process is defined in Cartesian coordinates, so we are going to rewrite them in that system. We use the usual change of coordinates. R equals the square root of the squared sum of x and y. Also, x equals r multiplied by the cosine of theta, and y equals r multiplied by the sine of theta. With that, we get the x and y component of the magnetic field, and given the x and y initial data, we can get the solutions. In this solution, the position of the magnet is antiparallel to the magnetic field of the Earth. Because of that, the field is repelled. Here it is parallel and it attracts. In this solution, the lines that connect the poles of the magnetic field of the Earth and those of the magnet are perpendicular. I hope you have enjoyed the presentation. Have a nice day and thank you very much.